Hello, everyone. Can you guys hear me?
Yeah.
Okay, so Mustafa, I might be your co-host today.
Okay.
So you should be able to, manipulate things the way you need to lecture.
Perfect.
So we'll start as usual with 11:10. At the beginning, I'll just introduce you for people that don't know or didn't attend your tutorial specifically, and then you can start.
Okay.
But we already recorded, so that you know.
So while we're waiting for the class to start, I hope all of you got in a chance to look at the project handout that was posted. So if you have any questions in regards to the project, feel free to ask right now.
Okay, I think we should start.
Yeah.
So for everyone, today we're gonna have, as was announced before, Mustafa, our TA, will be replacing me and giving this lecture, and I'll be here if you need any questions. So Mustafa, please take it from here.
Okay, so hey everyone, we're going to continue our talk on assembly today. Before we begin, just a few questions that were in the chat. So your project was out this week. Hopefully you've all had a look at it. Please start working on your project. Like there are some aspects that you'll be able to do after today's lecture, most of the project actually. But even so, just start planning out your project and working on it so that you have some progress by the time we have our check-in report. So on the last week of classes, you're going to meet with your TA and you're going to show what progress you have so far. And that just lets us make sure that you're up to or keeping up with the project and you're not like significantly behind. And if you are, we can give you the help that you need. Okay, so a quick recap on what you've done with assembly so far. So far you've talked about the different types of instructions. You've talked about arithmetic operations, logical operations. Last week we talked about branching, jumps, comparisons. We've done if and else loops, both in lecture last week and in your labs. So there's only a few more instructions that are left to look at properly. So importantly, we have the memory accesses and system calls. Most of you should already be familiar with the system calls, but we'll go over them today. You have been using them extensively in your labs. So let's start off with memory. So all of the previous instructions we've looked at operate on registers and immediate values. So how do we actually access RAM? And how do we actually work with RAM? You'll notice that the way we've designed the CPU is that all of the logical operations only happen on registers. So when we want to work with memory, we need to fetch values from memory into our registers. We work on the registers, and then we basically store the values back into memory. So that's going to be your usual workflow when you're trying to access stuff from memory. Memory instructions are I-type, so immediate, and they're generally of the form like that. So you'll either have a load or a store instruction. You'll have a data register, so where you want to load the data into or where you want to store the data from. And then you have this weird looking thing here. So you'll notice that all the memory instructions are in this form of you have a base and then you have an offset from the base. So the way this is laid out is that this register here contains the base address, and then this is the offset from that base address. And that's just how they're stored. And we'll go into the details of that in a second. A quick reminder, just if you don't remember on what these terms mean. A word, when we say a word, we refer to 4 bytes. A half word is 2 bytes, and a byte is just a singular byte. So with that in mind, here's all of the instructions that are available to you in MIPS. So you see that we have a bunch of instructions. So just going from the top, we have load byte, we have load byte unsigned, we have load half word unsigned, load word, and then store byte, store half word, and store word. So they're all of their opcodes, and you see that they all follow the same syntax we have here, with the base value and then the offset into that base. Just a few things to remember. When you say load byte or load half word, it takes the least significant byte or the least significant half word from the address you have. That's just something to keep in mind. Okay, so let's look at some examples to make this clear. So let's say we have this example. So that's load half word. We have a register T0, then an offset of 12 from the register S0. So what does that mean? It means load in a half word. So load in 2 bytes from the memory address S0 plus 12. So we take the memory address that's stored in this register, and then we add 12 to it, and then we load in the 2 least significant bytes from there. Once we have those, we need to signed extend that bit. And because we need to sign extend it, you'll notice that we have a signed and an unsigned version of this instruction. So just to determine how we want to extend it. And once we have that, we can store it into the register T0. And similarly, if you want to store something, so in this case, we have a store byte instruction. So that takes the least significant byte from T0, and it stores it into the memory address, which is S0 plus 12. So the same memory address as here. Any questions on how this works? So again, if you have any questions about this or in general, please feel free to just You can either turn on your mic and just interrupt me. I'm completely fine with that, or just ask a question in chat. I'm more than happy to slow down and go over something again if it's not clear. Okay. So why do we have this weird base and offset thing? The base and offset stuff is really useful when we're working with stuff like arrays and stacks, because it allows us to keep one single base address and then get multiple values using different offsets from it. We'll talk more about how structs work later on, and you'll see that this is extremely useful when we're working with structs like that. Just another thing, so memory is not just something we're going to use to store and write data from. We also use it to actually interact with different IOs. So if you've noticed, if you've taken a look at the project handout so far, we're interacting with the keyboard and the monitor all using memory. So this is known as memory mapped IO. So the way it works is that the inputs and outputs are basically mapped onto a section of your memory. So when we're working with the display in assembly, for example, all of the pixels on the display are going to be mapped to a certain region in memory. And if you want to write a color to the pixel, we basically go to that corresponding memory address and we can just write the color of a pixel, and then it updates the display. So in this way, we can use memory as an interface towards all different sorts of stuff. And the same way works with keyboards. If you want to read or write input. Generally, if we're trying to use keyboard or other types of IO, there's two different ways we can use it. So one of them is called polling. And specifically, polling is basically every so often you go and check that place to see if something has changed there. So that's the approach we're going to take on the project. You're basically going to constantly, every frame of animation, you just check if the user's put in some input. In that case, you read it. Another way to do it would be using interrupts. So we're not going to cover interrupts too much in detail in this course, and we're not going to implement them, but they're worth talking about. So what are interrupts? And in general, traps. So a trap is a mechanism to pass control from your program to the kernel. So there are many different types of traps. So traps can happen in case of exceptions. So if you have, let's say, an arithmetic overflow, and you can do this yourself in MIPS, you basically load in the biggest possible integer, and then you try to add something onto that. It's going to kind of crash your program. So it's going to have an exception, and it's going to be passed on to some special code inside the kernel, which handles that exception and then quits the program. What you can also do in METs, and we're not going to cover this again, but you can set up the keyboard IO to basically call a special kernel function every time there's a user input. So that stops you from having to explicitly check every single time if there's some input. And you can basically set it up so that whenever the user presses a key, a certain function of yours is called. And you can imagine how that would be useful if you don't want to constantly be checking manually if there's new input. A system call is basically a type of a trap, which we voluntarily call. So in case of exceptions and interrupts, we don't really manually call them. We kind of set it up so that whenever there's an event, it gets called on its own. Okay, so we have a question in chat on how memory mapped IO works. So the details of that are, they really depend on what sort of IO device you're working with. So the details of at least the bitmap and stuff are not particularly relevant to what we're talking about. The whole concept is that memory mapped IO serves as a sort of interface that whenever you write to the memory, there's probably some logic within the display driver or the keyboard driver that whenever there's a key press, it goes to that location and writes some memory. So it just serves as a common interface of sorts. Okay. Cool. So we'll talk more about interrupts and exceptions next week. So there'll be a section on that in next week's lecture. And more in general, it's something you should look into in MIPS if you're interested in this. MIPS does allow you to basically define your own kernel functions in there. Because we're running everything in a simulated environment, you can basically define your own kernel code to where the traps actually get called to. And you can do some interesting stuff where, let's say, if you make an arithmetic overflow, you can basically write some kernel code where it gets put into there, and then you can handle the process however you want. So that's something cool to talk about. And if you're interested in that, feel free to email me or ask me on Piazza, and I can point you to some resources about that. Okay, anyway, let's get back to system calls because we have actually used them. And again, you've used this a bunch in lab. So let's just briefly talk about them and then move on. The system call basically traps and gives control to the operating system to perform some actions that you want. We use the A0 and V0 registers to pass in the arguments and then the type of system call that we want to perform. And the table on the right just shows you some of the common system calls. And of course, depending on which environment you use, there's going to be different ones. So these ones specifically are for Mars or the Qt SPIM environment. And as an example of a system call, this is just some code. So we load in what type of system call we want to do into the V0 register. So in this case, we're putting in 4, which represents print string. Then we put in the address of the string that we want to print inside A0. And then we make a system call. And every time we make a system call, it goes and basically checks those 2 variables. So in this case, it would check V0 first. And it would see that, OK, the option is to print a string. In that case, it needs more input. So it goes and looks at A0 then, and it basically uses that input to print out the string. So any questions on system calls before we move on? I'll give you all a minute. OK, so if everyone's good with that, then let's look at arrays and structs. So let's take a step back first and look at how data is stored in assembly. So we have our .data section at the top. And in that section, you've already created different types of data. So let's talk about it in general. So a label or data is always defined in this form. So you have a label, you have the type of the data, and then you have the values of the data. So let's look at an example. So over here, var1, we're defining a word. So a word is 4 bytes. And then we're assigning that to the value of 3. In the second example, we're creating an array of different values. So instead of just putting in a 3 there, if you just put in a list of values separated by commas, it'll create a 4-element array in this example. Array 1, we're creating an array of bytes, a similar way. So the whole array here is going to take up 2 bytes. And the first case, it's going to take up 16 bytes because each of the elements are 4 words. What you can also do is you can manually just allocate some space. So over here in the last example, array 2, we're just basically allocating 40 bytes of space. And you can use that space however you want. You can use that space to store 10 integers or 40 characters or 20 half words. There's really no restriction. You can even mix and match if you want. Basically, because you're programming in assembly, all of the control is up to you. You can use the space however you want to. So just a reminder again, integers are 4 bytes and characters are 1 byte. Okay. So let's look at actually how arrays work now. So arrays in assembly are very similar to how arrays work in C. So I'm guessing most of you have already used C because you've done A48. So has anybody not used C before? If you can just let me know in chat. So just want to get some gauge of how many people are kind of familiar with this stuff. If not, we can go slower. OK, so if you remember from C then, an array is basically stored as the address of the first element. So if you want to get the nth element in an array, you first need to figure out where the address of the nth element is. So the way that's done is you figure out the offset from the start of the array. And then the way you compute that offset is you just take your array index and then you multiply that by the size of each element. So if you want the 5th element, then that's going to be 5 times the size of the element. And again, arrays when defined that way are stored completely in memory. And if you want to do some operations on the array, like add up all of the numbers, you need to fetch the array values into registers, you operate on them, and then you can store them back in memory. Okay. So just as an example of the indexing, let's say we have an array A, and that is 100 elements. And we want the address of the 5th element, so that's index 4. How do we compute that? OK, so Terry, I'm just going to walk through this. Maybe that'll make sense. So to compute this offset, we would say that the index is 4, and then each element is 4 bytes. So we take 4 times 4. So the offset here is going to be 16 bytes. So they get the address of the element at index 4. That's going to be basically the base address of the array plus 16. So, OK, some questions in the chat. So the first question is, the 5th element, is it 5x the size of the first element or the first plus 4? So it's not just the first plus 4. So it needs to be 4 times the size of each element, because each of these elements here is taking up 4 bytes. So that's 4 bytes. That's another 4 bytes. That's another 4 bytes. That's another 4 bytes. So the start of this element is going to be 16 bytes away from the start. And for all of the commands that work on memory, the addresses and offsets are all in bytes, not words. So that was the second question. Okay? Everyone clear on that? Okay. So if everybody's fine with that, let's do an example, and that'll help make everything more concrete. So let's take this piece of code that I've been hinting at this whole time. So we basically have two arrays here. Let's assume that they're somehow initialized to some values. And what we're basically going to do is we're going to loop over both of the arrays and then set the ith index of A equal to the ith index of B plus 1. Okay. So how do we write this in assembly? So before we just jump into the assembly code, it's important to slow down, and just take a methodical approach to writing this down. Because this might be easy, but once you start working with more complex arrays and maybe arrays of structs in the future, it's going to be important to try and break this down into a methodical process where you can just follow each step and you can be sure that your code works without having to spend like 2 hours debugging this. So the key to reading and designing assembly code is basically figuring out the high-level operations you want to do. So it's going to always be better to write down sort of in English what you want to do in each step and then translate those steps into assembly code. So let's try and do that here. So what are the things we want to do? First, we want to initialize everything, and then we want to perform the loop. Now, within the initialization, what do we need to do? So first, we need to allocate space for both of the arrays. We also need to store the initial offset, so the value of I, for example, here. We want to store the maximum value. So in this case, because there's 100 elements, it's going to be easier for us to just store the maximum offset. So instead of looping over the value of I, we just loop over the offset. And that's just going to save us a variable when we're looping. So we want to put both of these values in a register. And we also want to put the addresses of both of the A and B arrays into registers. Because again, remember, we need to use registers to actually load and store the values. Now, for the loop, what do we need to do? We need to put in the actual addresses of the ith element into registers. So we need to compute the base address plus the offset. Once we do that, we want to load in the value of the B index I into a register. We also need to add 1 to it. And once we're done, we store that value back into the A array, and then we update I. And once we're done with that, we can just check our loop condition and jump back to do it again. Any questions on the high level thing here? This should be a process of writing assembly code. If you have any questions here, you should stop and try to resolve them at this stage. And once you're done with this, writing the assembly code is fairly easy. There's a pretty direct mapping if you can break it down to this granularity. Okay, so if there's no questions, let's start actually writing the code. So for initialization, we first need to allocate space. So that's going to basically map to us defining in our data segment, A. So we say we need some space and we need 400 bytes because an integer takes 4 bytes. And we do the same for B. So we need 400 bytes for B. Once we're done with that, we need to do our initialization of the other values. So in our text segment now, let's add the value 0 to T0. So T0 is kind of going to be our counter variable or the offset variable. We also want to load in the maximum possible offset in this case. So that's 400. So let's put that in T1. And then we want to put in the values of the registers or the addresses of A and B into more registers. So for this, we can use the load address command, and we just give it the label we give to the space. And that's going to load in the address of A and B into T8 and T9. Yeah. So a good question in the chat. So somebody's asking, does I++ here mean I plus equals 4? Yeah, that's right. So I++ is basically, it's referring to this condition here. When we actually do the increment, we're going to have to do +4 because we're trying to do offsets. So a good question. You'll see that in a second when we look at the code. So once we've loaded in the address of A and B, we've done our initialization step. So let's start our loop now. So for our loop, we're going to have the first thing. So we're basically adding the offset from, so this is the address of A, and we're adding our offset, and we're storing that into T4. Then we do the same thing for B. So this is the address of A index I. This is the address of B index I. And we have those in T4 and T3. Then we can load in the value from B. So notice that this is loading in the value from address D3 with an offset of 0. We're putting it in S4. Then we add 1 to S4. So that's doing B index I plus 1. And then we can store that value back into A. And once we're done with that, we update our I. So to go to the next element, we basically add 4 to our offset to get to the next integer address. And then we can just check our condition. So if it's not equal to 400 yet, we can keep looping. So here's all of the code with the comments. So I'm going to pause here for a second, let you all have a look at it, and just make sure you understand it. You've already done the looping stuff so far. Just want to make sure that you understand how we're actually doing the offsets and indexing. So yeah, like integers as in, yeah, sure. Like it's just a memory address, right? A memory address is just a number. So you can treat them as integers, sure. Like they're just numbers. You can put them in a register, you can move them around. Did I answer a question, or were you referring to something more specific?
I guess just to clarify, remember all the assembly at the end of the day, it just becomes a machine instruction. Machine instruction doesn't understand anything else other than the positive integers, right? So at the end of the day, this is just a convenience for you to think about things. But at the end of the day, this is just going to be just a number.
Yeah, so whenever you write this sort of stuff, the offset and the address get added together, and it just gives you, it like spits out a number in binary, and that's all you see in your actual machine code. So the machine just operates on whatever that is. So this is just a more convenient way for you to be able to offset and like access stuff from an address. So all of this is just like syntactic sugar in assembly, basically. Okay, so any questions on arrays? You're going to be working with them for the next lab. So star A equals star B. So that would, yeah, so that is something you could do. So if instead of, okay, so that's a good question. So the question here was, instead of incrementing, instead of using this offset variable and incrementing that, can we just increment T9 and T8 by 4? So can we just add to that every time? Yes, you could do that. That would work exactly the same. It would just be a bit weird with then your loop condition. So for your loop condition, then you would need to make sure that your T1 register is the address of A0 plus 400. Okay, so you just have to be careful about that, but then you can do that as well. That works too. So there's many ways of doing it. This is just, this is basically the most direct mapping you can make of this code. And I think this one's just easier to read. So you can do it either way. Any other questions? No, you can't use B over there. So basically, this number here needs to be an immediate value. So this needs to be like 0 or an integer. You can't put in a label here. That won't work. So this needs to be a register. This also cannot be a label. And this needs to be an immediate value. So more often than not, when you're looping over arrays, like this value is always going to be 0 because you're using some additional value to like offset your thing. Because you cannot put in a variable over here. Like this cannot be a register as well. So if you need to loop over an array, you usually need to just have an offset variable that you're incrementing like that. You add your offset to your base address every time. And then you just index into that at like offset 0, basically, if you get what I mean. Yeah, so SW means save word, store word actually, and LW is load word. So W is for word, H is for half word, so that's 2 bytes. And if you see SB, that's going to be store byte or load byte. And then that has its signed and unsigned versions. So just a question. On our previous slide, we had signed and unsigned versions for both the load byte and load half word. Why do you think there's no unsigned version for load word? Does anyone want to answer that? So we have unsigned versions for load half word and load byte, but there's no unsigned version for load word. Anyone tell me why? Yeah, so there's no need for it. The reason you need to specify when you have a half word or 1 byte is because you need to sign extend them to put them in your register. Remember that all of your registers are 32 bits. So if you're loading in like half a word, you can't just put in half a word. You need to somehow, you need to make that into a 32-bit value to put it into the registers. So if you're loading in a smaller value than 32 bits, you need to extend that, and then you need to have some indication of whether you want to logically extend that or arithmetic extend that. When you're loading in the entire 32-bit word, it doesn't matter, right? You can just load it in, and it treats signed and it treats positive and negative values exactly the same. Just load in the entire word into memory. Okay. Any questions on that?
I just want to add some clarification to the Hans question early. This is not even related to this course, but mostly to understanding how the C language works. So you put star A and star B, and you kind of alluding to using pointers. Remember that even though semantically what you're going to do might be very similar, the code generated for pointers might be quite different, because remember, pointers might be allocated on the heap using malloc, right? System calls. So the code for them, I ended up looking, even though semantically it's going to be same thing, the assembly would look quite different, right? Because of the system calls you would need to use, right? While the arrays that are allocated, they're statically allocated, they're fixed size, right? So there is a difference, even though semantically it's the same. So don't get confused by that. So it's not absolutely identical. Yes, so that's what I thought. You might think it's absolutely equivalent. It's semantically going to do the same, but performance-wise might be quite different. Well, the examples of doing malloc is going to be quite long to fit on the screen, right? But Zehan, if you really want example, take a tiny piece of C code and generate, like even on your laptop, right, with some compiler, either using Linux machine or Mac machine, and then just, you know, compile it and look at the dump, and you're going to see what code it generates. You can just make a sort or something, like copy paste some examples from the web. You would see how the assembly would look like.
So if you want to try it out in MIPS as well, if I go back to my system call slide, you'll see that there's an instruction here to actually allocate memory onto your stack. So this is basically the malloc equivalent. So you can give it the number of bytes you want, and then it's going to return the actual address of the allocated memory. So this memory is going to be allocated on the heap, not in the global data section. So we'll talk about the actual memory model in a few minutes. But basically, it's going to be stored in a separate region of memory. So it behaves a bit differently. But yeah, you just get a pointer to it. So this is going to be a pointer like in C, and then you can manipulate it like that. Okay, cool. So that's fine. Let's move on to structs.
I think there's one more question there, Stefan. How do we know what type of extend is used?
How do you know what type of extend is used? Okay, so let me just go back to the slide where we had the memory instructions. So I believe that was on right here. So if you're looking here, if you have a load byte, that's going to be basically logically extended. If you have a load byte unsigned, it's going to be an arithmetic extension. Oh, my bad, I mixed that up. So if you have a load byte, that's going to be an arithmetic extension. If you use the unsigned version, that's always going to be a logical extension. So you extend with zeros. In this case, you extend with whatever the most significant digit is. And in the case of load word, we already said that it doesn't matter because we're loading in the entire word, so there's no need to extend anything. Okay. So again, it says here that this one is sign extend and this one is zero extend. So it's yes, Yang, that's exactly it. Like you cannot plus a reference to an array. Like when you pass in the array to a function, it basically it becomes a pointer, but it's a bit weird if you just statically define an array in C. So you kind of need to index it in if it's in the same scope. So it's just some quirks of C you need to be careful of. But other than that, like the actual offset stuff, it works mostly the same. So if you do load byte and the most significant bit is 1, it'll be extended as negative. Yeah. So if you do load byte, then it's just going to sign extend it. And sign extend just looks at the most significant bit and it extends it based on that. Okay. Cool. So let me go back to the slides we were at. Okay. So if there's no more questions about the array, let's move on to structs. So structs are conceptually fairly similar to arrays in the fact that we're basically storing a bunch of values one after the other. In assembly, there's no like explicit way of defining a struct. So there's no like struct or like a type def sort of thing like in C. So a struct in assembly is basically you just allocating a bunch of space and you using it mindfully. So you need to know how you're using the data. So to go through this, let's just look at an example and then try and understand how the struct is being used from an example. I feel like that's the best way to approach this. So let's look at this piece of code we have here. And let's try and answer what this code is actually doing. So anyone wants to take a gander at what it's doing? So you'll notice that we're actually using our offsets here from our store word notation. Okay, so no one. So I guess the key here is going to be to look at the store instructions we have. And you see that we're storing some values in T0, then T0 plus 4 and T0 plus 8. So each line is setting some value that's been set by the line before it. So in this case, we're storing a 5 into T0, and a 42 into T0 plus 4, and a 12 into T0 plus 8. So we kind of have a struct here, which takes up 12 bytes. And then we're storing in 3 different elements in our struct. So if we kind of wanted to take this program and kind of write a C equivalent to it, it might look something like that. Right? We have a struct with 3 integers. And how do we know these are integers? Because these are 4 bytes each. So they're kind of the size of integers. So this would be the C equivalent of that code. We kind of write a struct and then we put in the elements in there. Okay. The key thing I want to point out here is that there's really no like syntax in assembly for telling you it's a struct. It's just something you need to manually keep track of. What we usually do is we use this sort of notation for a single struct. So we keep the base address of the struct, and when accessing the different elements of that struct, you use offsets. It just gives you a clearer view of the fact that, okay, we're treating this T0 as logically the sort of one struct, and we're accessing different elements inside that struct. You could equivalently just add like 4 to T0 in between here and then do 0 T0, and that would work too. But this just serves as a way of like differentiating the fact that you're treating this as one unit and you're accessing values from that unit. And that becomes more important if you have, say, an array of structs, where between each iteration of your array loop, you want to move your T0 to point to the next struct. But then within that iteration, you want to use these offsets. And that just helps you get a clear picture of how everything is stored. Any questions on that? So I'm just going to have the same code here with some comments here, just to make sure you understand what's going on. And just to elaborate on that further, the first element of the struct is being set to 5. We're using indirect addressing here, using the offsets. And then the second element, which is at 4 plus T0. So remember that each of these takes 4 bytes. So that's at offset 0 from the start of the struct. That's at offset 4, and that's at offset 8. So we're just rolling the values in at those offsets. Okay. Any questions on how we would work with this? There's really nothing special about structs, which is kind of confusing because you would expect there to be, but you just allocate some data and then you use it carefully. Like that's all it boils down to. Like most of assembly programming is really just figuring out what data structures you want and how you want to store them. So for example, if you're looking at your assignment or your project rather, and you want to store the location of the platforms, you'd probably want to have a struct where you're storing, let's say, a character or a half word for each of the X and Y locations. And that would be in your struct. So you'd want to figure out how that's actually being stored, what the size of all of the data is. And once you have that design down, you can basically allocate enough space for it and then store it over there. So it's important to like logically map out what you're doing and what sizes you want your elements to be, so that you can carefully do this sort of stuff in here. Okay, there's no fancy struct syntax where you can just do like x.a or x.b. You're programming in assembly, so it comes with. Yeah, cool. Nice catch. That's exactly my next slide. Are there alignment? Yes, there are alignment issues. So the caveat here is that every element is, the address of that element needs to be aligned based on the data size of that element. So more precisely, let's look at this example where we have an int a character b, and then another int c. So if you're trying to put in some values into there like this, what you would naively try and do is you would say that, okay, I'm going to take my D0 address, and then at offset 0, I'm going to store in the value 5. Then at offset 4, I'm going to store in the value b. But since b only takes in 1 byte, I'm going to store in the next value at offset 5. That does not work. Because c is an integer, so that's a word, so that takes 4 bytes. The address of this must also be 4 byte aligned. So this will give you an error. Like, this will not work because MIPS doesn't like that. So C would need to be stored at offset 8. So you have some padding between there. If C was a character, then store byte with offset 5 would work, because a character is 1 byte, so it can be at any offset. But if it's a word, it needs to be 4 byte aligned. And if it's a half word, it needs to be 2 byte aligned. Yeah, so you would waste a few bytes. So what you could do is you could instead put in C over here. So if you put C at the start here, then you would use up all, there would be no padding in between. But then if you had an array of those structs, there would need to be padding between the structs. So one way or the other, you'd be wasting some space if you needed a few of these structs. Yeah. And again, the same is true for C code. It's just not really clear. So if you write something like this in C and you print out the size of that struct, you'll see that it behaves the same way. Why is there such a restriction? I'm not sure. It's probably got something to do with like how MIPS was designed to run on like actual hardware, and probably just something about the hardware where it doesn't like being stored into that. I guess Gennady can comment on why exactly the words need to be aligned. As far as I'm
it's a hardware restriction. So DRAM and cache is operated at a certain granularity. So it would be a huge waste. So essentially, if you allow that and people would do unaligned accesses, if you permit that, that will be very costly, right? You have to read, discard some bytes and things like that. It's not fundamental to the assembly itself. So for example, if you would work on something like new types of memory, like non-volatile memory, some of those memories are byte addressable. So any offset is possible, right? But pretty much in typical caches in DRAMs, they are word addressable, right? Hope this answers the question. Yeah. So this is more of hardware restriction that if you allow that to do, it's going to be very inefficient code.
I guess you all can kind of relate, because we've talked about caches and we talked about like the different block sizes in caches. It's always convenient to pull in the same block size for a particular cache. Like it's easier for you to pull in like address aligned block sizes so you can do the offsets and stuff like that.
So higher order languages might have things being misaligned, right? And then when you're going to debug why performance is lost, what you're going to see, there's a lot of code synthesized to fix the misalignment on the assembly. So yeah.
Okay. Any other questions on structs?
In fact, there would be even a penalty if you really want to look deeper into that. If you happen that the block you request is nicely aligned, but say your struct somehow crosses the boundaries of the cache lines. So your typical caches, not the toy examples we had, but the real caches are usually 64-byte cache lines, and your struct can be over that. So what might happen if you access something that is in between the two cache lines, it might trigger some misalignment issues, right? It will be handled by the hardware properly, but there's going to be a penalty for that. Yeah, please go ahead, Stefan.
Okay, so I guess the next section we're going to have is on functions. So to not break the coherence of the lecture, if there's no more questions on any of this stuff so far, let's take a 10-minute break. Like we're approaching the 11:50 mark. And once we're done with that, we can just jump into functions and finish the rest of the lecture, like together, without breaking in between. Everyone okay with that?
It should be fine. So,
okay.
So come back, I guess, at 12, right?
Mm-hmm. Yeah. Okay, so hey everyone, if you're back, let's begin the rest of the lecture. So we're going to talk about functions for the rest of the lecture, and then we'll have some other insights on stuff that we've talked about today. So if you're not here, please let me know in chat so I can wait for you. Okay, no one, so let's move on. So let's look at a function and see the different things we need to keep in mind. Give me a second. Okay, so here's a function. So the simple function that we're going to try and implement later today, it just takes in an integer and then returns the sign of the integer. It'll return either 1, -1, or 0. So we have a function, and there's different things that we need to take care of in the function, and we need to handle them. The first is function arguments, and then the second is the return value. We know how to do intermediate computations and stuff like that already. So how do we handle stuff like this? The first question is, where are the function arguments actually stored? So what we're going to do is we're going to store these functions at a certain location in the memory, which is called the stack. Now, again, just remember that there are other conventions to do this. So for example, what you could do is you could store the first 4 arguments in the registers A0 to A3, and you can store the rest of them in the stack. My more general point is that there's many ways of doing this. Because you program in assembly, you have full control over your code. So there's like at least 10 different ways I can think of that you would call a function. What you want to usually do is define a convention so that when you're working with other people on a project, or even if you're working yourself on a large project, you want some consistency between how functions are called so all of your code can work with each other. So what we're going to do is define a convention and then stick with that convention for this course. However, there can be many different conventions, and because you're writing the code, if you think that writing some code that breaks the convention but works better is good, then you're free to do it. Okay, so let's take a quick look at the memory model first. So here's our memory address space for our program. So you'll notice that on the top, we have our operating system code. On the bottom, we have the actual code for the program. So that's your .text segment. Then you have your global variables here. That's your .data segment. You have your heap, which is all of your dynamically allocated memory. Then you have your stack here, and in between is allocated space. So in particular, your heap grows up. So when you dynamically allocate memory on the heap, it grows up from the bottom, and your stack grows down from the top. And because they share the same space, if you allocate too much memory, at some point they're going to collide. And when they collide, you get a stack overflow. So yay, you know what that means now. And I just want to point out again that the stack grows backwards. So it grows from the top down. So if your stack pointer, so a stack pointer is basically a register that stores this address here. That's the end of the stack. If the stack pointer decreases, that means your stack is becoming bigger because your pointer is going down, so your stack is becoming bigger. And then if your stack pointer increases, your stack is becoming smaller. Okay, cool. So where do we keep the arguments of the function now? So we need to pass in arguments to the function. So why do we keep them in memory? The reason is because there might just not be enough registers. And in this case, for this function, we have just one argument. So we could store them in memory. But in general, a function may have many different arguments. So you have more arguments than. If you have a really long function, if you looked into the kernel code, for example, some functions take in a lot of arguments. So you might not have space for them. And perhaps the bigger problem than just having a function, let's say 32 arguments, is that functions all usually call other functions, and then they might call other functions. You might have a whole layer of different layers of function calls. And whenever you call a function, you need to load in the values of the arguments for those functions into registers, and you need to remember those values, right? So even if my sign function called another function, and let's say there were 10 function calls like down the line, but all of those functions return and I get back to this sign function, I still need to have this value in memory. So basically, if I'm using a register for this argument, I can never use that register again. So I'm really limited on the number of registers. So in general, I want to use memory to handle sort of situations like that. Just a note again, you can use the registers if you can basically guarantee to yourself that, okay, this function is never going to call another function. I'm never going to need more than one register. So in the case of this example, exactly, like you know that, okay, this is never going to call another function, and I'm never going to need more than one register for the argument. So you could potentially just skip the stack completely and use a register for this. As an assembly programmer, you get to make these decisions. So you can say that, okay, my function is small enough where I don't need to use the stack. I can basically save myself from reading and writing from memory, which is slow, and I can just use the registers directly. If you're writing in a higher level language like C or even Python or anything else really above C or including C, the compiler makes these decisions for you. So in general, if you're writing a language, if you're writing a program in C, for the most part, the code is always using the stack to pass in arguments, because the compiler can't make any real concrete guarantees about what your code is doing, because it doesn't know what you're intending to do. It only sees the code. So it basically defaults to using the memory because it's the safest option. Okay. So if you want efficiency and you're programming in assembly, you can make these optimizations. So that's why assembly is good. And that's why people still program in assembly when you need performance. So now how do you access the stack? So the top of the stack, so basically the boundary where the stack ends is denoted by a special register. So that's SP, so that's your stack pointer. And you basically use this to access the stack. So for example, if you want to push in a value into the stack, you first want to move the stack pointer down. So you move it down by subtracting 4 from it. So that if you want to load an integer, you need to subtract 4. And remember that when you move the stack pointer down, you're actually making the stack bigger. So once you've moved it down, you have some space for it, and then you can put in your actual data into that position on your stack. And similarly, if you want to pop a value from the stack, so you want to take something out from the stack, you first load in the value from the current stack pointer, and then you move your stack pointer up to denote the fact that your stack is shrunk down. Okay. Any questions on that? So just to make it clear, let's look at some diagrams because they usually always help me. So over here, the stack is just inverted so that it looks like a better stack. So the high addresses are on the bottom and the low addresses are on the top. So this looks more like a stack. Each of these blocks represents 1 byte, and this is what our stack looks like. So the stack grows upwards in this example because we've kind of flipped it, and your stack pointer points over there. So when you want to push an address onto the stack, let's say you want to run that instruction like we had earlier. So first, we move the stack pointer up by 4 units. That basically puts all of these blocks as part of the stack. So your stack is now bigger. And once you've done that, you can push in your 4 bytes at the location of the new stack pointer. And it's going to use the 4 pink bytes over here for your new value. And similarly, when you want to pop off values from the stack, you first read the value from the pink bytes. Then you move your stack pointer down again to denote the fact that your stack is shrunk. So that's your new stack. And then you've read those 4 values. So a question in chat. So how does this affect function calls? So I'm not sure what you mean. Like, why would this affect function calls? Can you elaborate? Yeah, so like, it's not like you're automatically decreasing the stack. There's nothing else going on in the background. Basically, the stack is denoted by SP. So if you decrement SP, that's just the size of your stack. There's nothing secretly happening in the background. Yeah, so functions are implemented using the stack, but you're the one that actually manipulates the stack. So we'll go through an example right now, but like it's not that whenever you write a function, there's automatically stack stuff going on. You're basically manually reading and writing values from the stack. So that'll become clear as in a minute. I'm just going to go over an example, okay? But yeah, the whole point is that the location or the value of the stack pointer determines the size of the stack. So if you're changing that, that's just going to determine the size of the stack. There's no like secret background. Like if you're writing assembly code, you're the only person who's using the stack. So as long as you're consistent with how you use the stack pointer, everything is fine, okay? The stack just serves as a bunch of memory for you to use. There's nothing really special about the stack, okay? So let's look at what we have so far. So far we've talked about taking our values and passing them into the function. Then we go to the actual function using our jump instructions. We compute all of the data. And now we want to figure out how do we actually return the data. So how do we pass in the return value to the caller? again, we can just use the stack. Okay. The other question is now, once you want to return from the function, we need to figure out where to actually return to. Because remember that the return instruction is basically just changing the program counter. So we need to somehow store the address where we need to return to. Okay. So that's going to be a return address. So again, if you've already looked at the lab so far, I guess you have an idea that that's going to be a return address register. So we talked about that. So once we're at the end of the function, we would simply just do jump to register RA, and that's going to jump back to the register. Now again, this is not the only way to do it. This is just a design choice. The register is there for convenience sake and for the sake of consistency, but you could technically just use anything anywhere. So you could also store it in the stack if you wanted to. But the jump instruction works from a register, so it's easier if you have it directly in the register. Okay? So what's the whole story here? So when you want to call a function, you first need to, the caller needs to push in the arguments to the function onto the stack. Then the caller also needs to store in the return address. So the caller needs to tell the function, once you're done, get back to this position. So it puts that value inside the return address register. Then it actually calls the function. And then the callee needs to first pop in all the arguments from the stack to actually use them. Once it's popped all the arguments, it can compute the return value. And once it's returned the value, once it's computed the return value, it pushes the return value back onto the stack. And then it returns. And then the caller function can take the return value back from the stack and use that. Yeah, so a function call, so to speak, is just going to be a jump instruction once you've set everything up. Okay, so once you've put in everything onto your stack, you just jump and link, and that's going to be your function call. So nothing is done by assembly, right? Like you're writing still all of the code. Okay, the whole function call is just the procedure of setting up all of your arguments on the stack and how they're handled. Like that's what a function call essentially is. At the end of the day, you're just jumping to a memory address to run the code. Okay? Did that answer your questions? Okay, so, and then of course you move on to the next line once you've got the return value. So let's look at this code again and let's try and actually translate it into assembly in case you're still not exactly sure what's going on. So remember, these are the 5 steps we basically broke down our function call into. So let's translate that step by step now. So again, this is all inside our text area. So first, so this is the code for the function. So how does that work? So once we've jumped this position, we want to load in the arguments from the stack. So this is what the first line is doing. We're saying take the stack pointer and load in that value from the stack pointer into the register called T0. So that's going to be our argument. Once we're done with that, we basically increment our stack pointer. So that's saying we've pulled the argument off the stack, so we can decrease the stack size. Once we're done with that, now we basically just have the code to implement this if statement. So I'm just going to rush through it a bit, but if you're confused, you can just look at the flowcharts we did from last week. So the idea is that you just check if it's greater than 0, you jump to a tag called greater than. Otherwise, if it's equal to 0, you jump to a tag called equals to. If none of these are true, then we must be in this condition. So we're going to store -1 inside our T1 register. So intuitively, T1 is the return value we have. And then we jump to the end. Otherwise, if it's greater than, we add 1 to our return value, then we jump to the end. Otherwise, if they're equal, we put in 0 in the return value register, and then we just go to the end. Now, once we're at the end, we have a return value in T1. We need to put it onto the stack. So first, we need to make room on the stack. So we add -4 to our stack pointer. So that brings the stack pointer down, which increases the stack size. And then we can push the element onto the stack. So we're just storing the word onto the stack. And once we're done, we can just return to the return address. Okay. And again, this is just the code with all of the comments. Any questions on that? I know I rushed through it a bit, but hopefully it makes sense. If you're stuck, let me know. We can go through this again. We have some time. So would not decreasing the stack pointer potentially override something? So not decreasing as in, so you mean in the end? Yeah, so over here, there's also other stuff on the stack, right? So in this case, there's nothing else for the context of this function, but whenever you make a function call, you put in arguments onto the stack. So let's say the signed function was being called from another function. You would have data from the other function on the stack. And I'll get to that in just a second. But yeah, you want to make sure that whenever you're writing something, you're always making room on the stack. You don't want to overwrite something because there will be useful information. And I'll get to the nuance of that in just a second. So that's a good question. I was hoping somebody would ask me. But does anybody see a problem with this so far? So we've basically said that we're putting all of the arguments from the function onto the stack. We're putting the return value onto the stack, but we're storing the return address just in the register. So there's a problem with this. It doesn't always work. Can somebody tell me when this breaks? Yeah. So what happens if there are multiple function calls? That's a really good question. So in reality, you don't always have the case that your main thread of execution is just calling one function. You're going to have functions that call other functions that call other functions. So how do we deal with that? Okay. So the key here is that we also store the return address on the stack. Again, I think this is, so in lab 10, you're going to be doing this again, but it's not just the return address that you need to store. Remember that in each function, you also have some temporary variables, and those temporary variables are stored in your registered. So you could be using the T0 registers, etc. And if you're making an arbitrary function call to something else, you don't know which registers the other function uses. Okay, so you have no guarantees about what registers the other function is using. So you can't just put in the parameters onto your stack, put in the return address on the stack, and then just call the function, because it might override all of your local variables you have. And by the time the function returns, you won't have any of those local variables there anymore. They might have been overwritten. So how do we overcome that? We basically also put in all of the temporary register values onto the stack. So the idea is that when you're calling in a function, so let's say you're in some function foo and you're calling in a function bar, before you call the function bar, you want to save all of your temporary registers onto the stack. So you put them in some order there. Again, you determine which order, and you just need to make sure that you restore them back later in the same order. So you'd save all of your temporary registers onto the stack. Then you would put in the arguments to that function on the stack. You would then you would call the function, and then once that function is called, you get the value from that. Then you restore all of the variables from the stack. Okay, and the temporary variables here will also include your return address. So basically, every register that's in scope that you're using, you need to put it onto the stack. Does that make sense to everyone? Basically, in general, you can't make any guarantees about bars. So you want to basically back up everything onto your stack. So if you're implementing a recursive method, for example, this is what you would want to do. Again, I'm not going to cover that too much in detail for now, because that's going to be part of what you're implementing for the next lab. So we want you to try that out. We want you to try that out on your own first. And then we're going to go over it in detail in next lecture. So Gennady is going to go over that next week. So we'll walk you through an example of how to do recursion. But yeah, so a question in the chat is, what if you have structs as local variables? Yeah, that's a good question. So if you have a struct as a local variable, so how would you have a struct as a local variable? Because like your local variables here, I mean as registers. So if you have a struct somewhere, that struct is going to be it's probably going to be defined in your data section, in which case it's a global variable. So it's not stored on the stack, so to speak. Or if you've dynamically allocated your struct, it's going to be in the heap, but you might have a pointer to the struct as a local variable. So that's something you would want to store on the stack. Okay. Like the problem with your question is that you can't just allocate like some random amount of space on the stack, or rather you can't just randomly have a struct that's inside there. Like you can allocate some memory on the stack. You can allocate basically any amount of memory you want on the stack. So you can like move your stack pointer by, let's say 4 or like 12 bytes, and then you can put in 3 integers there, and you can treat that as a struct. So remember how we said that a struct is not really like a separate thing in assembly. It's just a bunch of values put together, and you know how they're put together. Okay. So storing a struct on the stack is the same thing as just putting in a bunch of different values on the stack and just knowing which order they're put in there. Okay. Does that answer your question? So use case differences, not much really. So when you're writing assembly, you're free to use them however you want. Like traditionally, they're given some names just to like, that's mostly convention. You shouldn't really assume anything about them. It's mostly just convention. If you're using T0, like T0 should be like your first go-to variables for temporary variables, and then you can use your S variables, but there's really no restriction. Again, even if you look at x86, like there are some variables that like are recommended to use for certain things, but for the most part, like if you're writing assembly code, you have full control over everything. So as long as you're consistent within your code, it's fine. The conventions exist just to make it easier for you to keep track of what's going on where. Okay. And in general, like within a function, you know what variables you're using, so you just want to back them up onto the stack. Yeah, you don't particularly need array. Like you can always just use the stack to store the return address. It's just convenient to have the return address stored in array. So one of the reasons is that like your jump and link instruction, it always defaults to using the RA register. So it's nice to have a dedicated register where like the return address always goes to by default when you use the jump and link instruction. It could also be set up so that the jump and link instructions writes it to the stack. But the idea is that if you have a function, so like if this function is not calling anything else, that saves me an access to RAM. So I don't need to like actually write it to the stack and come back. So if this is a single level function, I can just use the return address thing. And only when I'm calling another function, I can write it to memory. So writing to memory is expensive, so it's also better to avoid it when you can. Okay? Like there's no particular reason for using exactly array. It's just convention. Like you can use another register if you really wanted to. Okay. Any other questions on functions? So again, that's pretty much the entirety of functions. So a full function would be, in this example, let's say bar was being called with arguments. Foo gets called with some arguments. You pop all of the arguments for foo from the stack. You do your computations. You store all of the registers that you're using inside here right now onto the stack in some predetermined order. Then you push in the return address for this function onto the stack. Then you push in the arguments for bar onto the stack. Then you call bar. When bar does its thing and it returns, you want to get the return address from the stack first. So you get the return value from the stack, from bar. After that, the last thing you put on the stack here was the return address for the current function. So you would read that in. Then you would restore all of the temporary registers that you were using back. And then you move on to the rest of your code. Okay. So it's just a bunch of different memory accesses. Okay. So what did we learn? This is one convention that we've defined. Now, again, there's many different ways of doing it. You can make it so that you're like as an example we gave earlier, like the first 4 arguments are always put into A0 through A4, and you don't use them for anything else. That's another convention you can have. It all depends. This is the convention that's mostly used because it just doesn't make any assumptions about what the other functions do. So you just store everything on memory as a backup in your stack. Okay. The other thing we learned is that function calls don't happen for free. There's a lot of manipulating of the values. So like there's a lot of different memory accesses. You're accessing a lot of variables. So function calls are expensive. And each of these different things, such as writing stuff to the stack, loading stuff from the stack, changing your stack pointer, all of them have performance implications. This also tells you why inline functions are faster. So what are inline functions? Basically, an inline function is when the actual assembly code for a function you're calling is not stored in as a separate function. So the assembly code for that function is put in line with the rest of your code. So for example, if the sign function from earlier was inline, you basically take the generated assembly for the compute value for computing the return address, and you just put it like right in between the other code instead of like making a function call. So that saves you all of those memory accesses. But again, that's not something you always want to do. So again, anybody tell me why you would not always want to inline a function? So the way I put it, using the stack is expensive. And putting all of this stuff on the stack is expensive. So ideally, I mean, for performance, you would just never make a function call, right? Like you compile on all of your code so that the actual assembly code for each function is put like directly in line with the rest of the code. What's the problem with that? So I've told you why you should use inline. Why would you not want to use inline? What could go wrong if you're using inline? If you just try and inline everything. Yeah, so what happens when the function is very long? Well, not enough registers is not necessarily a problem. Like you can still use memory. Like you can still use the stack to store some variables. So you can like kind of back up anything that you can't put in registers, you put that on the stack. So like that's not necessarily a concern. You can always default to memory. That's what it's there for. Because like generally you won't always have enough space to store in all of your registers when you're computing something. So what happens if you just inline everything? So I think Jiasheng pointed out that when a function is long, it gives you, there's a problem. But what's the problem? What if you're calling the function in like 100 different places? That's completely reasonable if you have a large code base. You're duplicating all of your code everywhere, right? You have a really big binary. And maybe storage is not that big of a concern. But we've also talked about how we have caches for instructions and stuff. So if you have a whole bunch of separate instructions, you're also now affecting your cache when you're trying to like pull in instructions from RAM. You're having a lot more like accesses to memory to actually read those instructions in, because each instruction is now different for each of the different function calls. They're in a different location. So you have a lot more memory accesses for reading. So in general, like if your function is really long, you only want to inline a function where the cost of the function, like the function is very small, so to speak. So it's a fast function and the memory overhead is a lot, right? So if you had a function where you need to like pass in 3 parameters, but it does like a lot of compute, it doesn't necessarily give you too much of a benefit to inline it, because the bottleneck there is not actually the function call. It's the actual computation that's going on in the function. Okay, so inlining is good for short functions that are like performance critical. They're really short and like they don't need, like they're not really long and they're not like have many nested function calls. They're perfect for that. In general, if you have a long compute function, which is not bottlenecked by the actual function call time, you're better off just leaving it as a regular function and then using your stack for it. Okay.
I guess there are some other reasons why you don't want inline functions.
Yeah, those are mostly to do with like cache thrashing and all of that stuff.
But there are some conceptual things. So for example, if you had a recursive function, then inlining doesn't have really that much.
Yeah, the recursive functions are out there. Like they cause problems with everything, but yeah. So you can see why like inlining a recursive function would be weird, right? Because if you're just putting the code in there, you somehow you need like a separate sort of stack for yourself to actually do that recursive function in a loop if your compiler was trying to be smart about that. If you're not trying to be smart, then it's basically not doable then. Okay. And in general, like the point is that all of the stuff that you do like has some sort of performance implications. And it's not just function calls, it's even like branches and stuff like that. So for example, let's look at 2 pieces of code. So you have a naive code and you have a better piece of code. Right? So in the naive code, where we basically have a counter and then we're looping over values in a list, and then we check, okay, if that element mod 2 is equal to 1. So if it's an odd number, we increment our counter, just counting the number of odd values in our list. Okay, this is good. It seems good. A better way to do this would be to do this, however. So instead of you try and remove this if condition. Why do you remove the if condition? Well, having an if statement introduces more branches. So in your code, like you need to do a comparison, you need to do a branch. In this case, you're just doing a comparison and you're doing an addition. There's no overhead of like having different labels and then jumping to the different labels based on your conditions. So in some sense, the assembly code is shorter, so it's easier to reason about. And it's also faster because you're not dealing with branches. And in general, branching or jumping is less efficient than linear execution. It's not just because of the reason I told you, and it's also to do with the fact that modern processors do a lot of prefetching. So if you're executing a line of instructions, the next line is usually already loaded in from memory before you know what line you're going to execute. So let's say you're running a bunch of commands. If you have a jump somewhere, your computer is already trying to predict what line you're doing beforehand, and it's going to try and run that instruction. This can work because when you're reading from RAM, you can kind of parallelize all of your reads from RAM. I'm not going to go into the details of that because next week is all about parallelism and pipelining as well. So that's half the lecture next week. So I'm not going to go into the details of how that works. But just take my word on it for now that your computers are trying to fetch an instruction and basically speculatively figure out what instructions are going to run next and then run them earlier. So it's a speed boost. So basically you don't have to wait in between each instruction for your RAM to return the next instruction to you. But then if you don't have the correct function, or if you didn't predict the correct line to run next, you basically need to redo all of the computation or go back, and that can be very expensive. And you're wasting a bunch of compute there. Most processors today have these things called branch predictors. So basically they look at the code around, and within the context, they try to predict whether the branch is going to evaluate to true or false. So every time you have a branch if equal, it's trying to predict which branch is correct. And then it tries to evaluate that before the actual condition is computed first. So there's a lot of speculative evaluation going on. Most modern branch processors have a greater than 90% accuracy. But even then, you can imagine that when your branch predictor goes wrong, you've probably evaluated a whole bunch of instructions before that. I'm not sure if Gennady's mentioned it to you already, but your RAM is very slow. So usually you read from RAM. If you miss in all of your caches, the read from RAM is going to take like upwards of 1,000 cycles. So it's beneficial to try and predict which instruction is going to go next, and you can basically preload the instruction from RAM beforehand. So if you've got the correct instruction, if you predicted the correct instruction and you ran that instruction, you've basically saved yourself thousands of cycles of waiting for the next instruction because you kind of predicted and you already have the correct answer. Now, of course, the downside is if your prediction is wrong, you need to go back and change all of that. And if you're really, really trying to optimize your code and you know how your branch predictor works, you can write your code in such a way that the branch predictor is more likely to be correct. And if you can make your branch predictor more likely to be correct, you can really speed up your code. Just as an example, I was looking at this talk of somebody trying to write a ray tracer in C++, and their code wasn't running too fast. So they basically spent I think 2 hours looking into what's happening. And they figured out that the branch predictor was behaving weirdly. So all they ended up doing was rewrite the if statement to change the order, and then their code ran 2x faster. So there's non-trivial performance improvements to be had if you understand how your branch predictor works, and you can write your code to properly utilize that. So this is an example. Let's look at 2 pieces of code. So one of them is basically going over the numbers from 1 to 10,000 and it's printing them. Okay, we have this piece of code, and then we have this piece of code. Which one do you think performs faster? Yeah, the second one. You're basically eliminating a lot of branches. And if you remember your while loops, how you implement them, you basically need to have a comparison and then a jump every single time you're doing an iteration of the while loop. this has like 10 times as fewer jumps and comparisons here. So you're saving a lot of time when you're writing it this way. Of course, the binary size is bigger. Loop unrolling is a common way to boost your performance. Now, again, this is not something you can always do, right? This is a really nice while loop, or basically guaranteed that nothing is changing. But when you can do it, it gives you a decent amount of performance improvement. Modern compilers are usually smart, so they try and figure out if this is something that's possible with your code, and they'll do it. But if you're writing assembly code as well, like you just want to remember that instead of if you want to do something 10 times, instead of writing a loop to go over 10 times, the faster thing would be to literally just copy paste it 10 times if it's just 1 or 2 instructions. So that's a faster way of doing it. So that's just stuff you want to keep in mind. Because hardware is very, very complex, and trying to understand hardware and write software that works well with hardware is actually very hard. It brings me to this quote that is by Alan Kay, and then Steve Jobs quoted it. People who are really serious about software should really be making their own hardware. And I guess right now that's more relevant than ever. With Apple's new processor coming out, they have some like really, really high performance for the amount of power they're using. So there's a lot of efficiency that they have compared to like them working with Intel. And the reason is just that they have basically full stack control. So then like all of the people who are writing the software know exactly what the hardware is doing. So it's much easier to write optimized code that runs much better on your hardware. Okay, so yeah, hopefully some of you get into software a lot and then start making your own hardware, and then we have cool hardware in the future. So yeah, that's all I really had for the materials for today. And I have some practice problems, which I intended to save for you all so you can do it when you're going home. But instead, let's try and do them now. So the practice problem we're going to try and do is implement this function, so stir copy. So I'm going to give you all, let's say, 5 minutes or so. So I recommend you all just like pull out a piece of paper or like open up a code editor and just try and do this yourself. And then we'll go through the solution I have in mind. Why? Just for practice. Like the more practice you get with arrays and writing functions, it's going to be easier for you both for next week's lab when you're doing like recursive functions, as well as just for the project, because you'll want to be writing everything down in terms of functions and loops just to make it easier for yourself. So yeah, I'll give you like 5 minutes or so, maybe a bit more if people are not done. So please try and attempt and write down the assembly for this, and then we can compare our answers. Okay. And in the meanwhile, if you have any questions about anything we covered in today's lecture, feel free to ask me, and I'll be more than happy to answer them. If you're attempting this and you finished converting this to assembly, please let me know in the chat. And I guess when enough people have finished it, we can go look at the solution. And you could do this at home, but I know that none of you actually want to sit down and do assembly at home on your free time. So we have some time now, so let's just work through it together. It'll be helpful to everyone. Okay, so just to get an idea, is anybody actually doing this and do they still need more time? If you actually want to complete this, let me know. Because if nobody's doing it, then there's no point of me just waiting here staring at the screen for you all to finish. If you're still doing it, let me know in chat and I'll give you a few more minutes. Okay, cool. So I'll take it up at, let's say, 12:45 then, so 3 more minutes. So Kevin, are you fine if I take it up now? Anybody else still working on it? Like if you're mostly done, that's fine too. You can just compare your solution and see if you're on the right track. You'll have more than enough practice with the labs anyway. Okay, I don't see any objections. So here's the solution I had. So let's just go through it step by step. So first, I guess I don't have the actual program here, so that's a bit annoying. But anyway, remember that we have, let's just look at the program first. So we need X and Y from our parameters. Then we have a counter for I. And basically while X and Y, so we copy X, we copy Y onto X while the values are not equal to the null terminator. So the value of that in ASCII is just 0. And so while that's not true, we also increment I. Okay, so that's a basic for loop. So that's equivalent to saying while Y index I is not equal to null terminator, X index I equals Y index I. So of course, if we're writing a function, first we want to pop off X and Y from the stack. So we read X from the stack into A0, and then we increment our stack. So it depends on how it was stored. So that depends on how you're calling the function. So if you, in the function, if you want X to be popped off first and then Y, you would put them in the other order. So again, if when you're writing the function, you just need to be aware of this. So in this example, you would assume that Y was put in first and then X was put in from the caller function. Okay. So again, that's up to you in which order the arguments go in. You just need to be consistent with that. So in this case, X is at the top of the stack or at the bottom because the stack is going down. Anyway, so you pop off X, then you add 4 to your stack pointer to make it to basically get that space back. You pop off Y, and then you increment your stack pointer again. Then we're initializing our counter. So S0 is just going to be our offset, so to speak. So that's 0 to begin with. Then we add x. We add x plus our offset and store it in T1. So that's going to be the current iteration of x. And we load that byte in. So T2 is now equal to x at index I. Then we're adding the offset to the value of y. So we're getting the ith index of y. And we're setting that to T2. So basically, we're copying the value from x into y. Does that seem right? I think the comments, I think this is actually in a different order. We should be copying from y to x. So I haven't actually run this code. Sorry, I should have run it. But it looks like it's being done in a different order. So in this case, it's taking the value from x, storing it into T2, and then it's storing it into y. So it should be the other way around. So I apologize for that. But you basically just switch which registers are being used. That's not too big of a deal. Anyway, so the actual strcpy function is not like the focus of this. You're already familiar with loops. Just understand that the indexing is being done with the offset, and then you load in that byte from that address. And remember, we need to load in the byte because the characters are each 1 byte. Okay, so we're not doing a load word here. So you want to be careful about which load function you're using. So once you're done with that, you store it in there. And then you just check if the T2 register is equal to 0. So that's going to be your current y offset. And if that's equal to the 0, that means your string is over. So if that's equal, you jump to your end. Otherwise, you increment your I. And in this case, we're incrementing I only by 1 because each character takes 1 byte. So you want to go literally to the next byte, which is also the next element. And then you jump back to L1. So this is your loop section, L1 to jump. And then whenever your y hits your null terminator, you jump out to L2. And then over here, you have you're basically not returning any, you're returning I, so you're returning the length of the string, so the amount of characters that were copied. So in this case, that's going to be an S0. So you basically make room on your stack again, so you increment your stack pointer by -4, and then you save S0 onto your stack. And then you can just jump back to the return address. Okay? Any questions on that? Other than the slight mismatch between the x and y's. But again, the main point here is to understand the indexing and the offsets and the function and loading in the values for the function from the stack. So any questions on this? You have, so when you jump, you have program counter +8. Is it +8? Maybe I'm misremembering. Are you sure it's program counter +8? It should be 4. Okay, unless the instructions are 8 bytes, but no, I think the instructions are 4 bytes. It's 32-bit. So that's interesting. I'll have a look at that and get back to you on Piazza if you can ask that question. It should be 4 bytes to get to the next instruction, but maybe I'm missing something. So if you can ask that on Piazza, I'll have a look at the reference and get back to you. Okay, it's a good question. Anything else? So I guess the main focus is, did everybody want to understand how to actually use the stack to pass in arguments? And then also how we use the stack to store in the temporary variables, etc., when we're making function calls. And then the second one is, did everybody understand how to properly use arrays and how to offset into different elements of an array, and how basically a struct is very similar to an array in the fact that we just have some allocated space and we're storing elements in that space. So this should give you pretty much everything you need to know in order to complete the project. We're going to talk about more stuff like recursion next week, and then some interrupts and parallelism next week, but none of that is going to really be relevant to your project. So basically from now until December 7th, when it's due, you have almost 3 weeks with everything that's covered. So again, I made a post on Piazza talking about this, and it shouldn't be too hard to do. I think the biggest hurdle you're going to have is to sit down and figure out how to lay out your code. So where does the data go? How you're actually managing your data. So which registers store what values, and then where in RAM you're storing the locations of what, etc. That's going to be probably the hardest part, and then you just need to sit down and code it out. Okay. And I suggest you make it modular. So if you have nice reusable functions for everything, it's going to make your life a lot easier. Okay. So yeah, if there's no more questions, yeah, that's it for today. I guess I'll see you all, whoever's in my practical section, I'll see you tomorrow. Otherwise, good luck on the quiz this week. And I'll stick around for the next few minutes, just in case somebody else is around and they want to ask me something. Otherwise, goodbye. Have a nice day.